Glacier lecture number 2. Again, this is chapter 14 in our textbook. And today we're going to talk about how they erode the landscape. And what's pretty amazing is this happens quite quickly. In the last ice age, for example, in Canada, about 30 meters worth of erosion occurred. So 30 meter erosion last ice age. This isn't true in every location, but this is just an average across parts of Canada, which means in a period of 10,000 years, we're able to remove 30 meters worth of material. That changes the landscape to negative topography, but then that material has to go somewhere and it gets deposited somewhere else. And so we have this change in landscape by erosion and by deposition. The mechanism for this change is twofold. All right, so we got mechanism of erosion. That's what we're going to have as our first heading. We have a 1 and we have a 2. In fact, we're going to draw a drawing here. Here's the substrate. I'm drawing this broken here, and then we're going to go downhill. Here is our ice flowing over the surface. Let's put a couple crevasses in. So we learned about crevasses last time. And this ice is plucking and abrading the material below it, and it's carrying rocks. Here's some rocks. I'm drawing in now the ice, and some of them sit along the surface here, and they drag along and they abrade. And then other places, ice gets into areas of rock and will pluck it away, and then we'll carry those chunks further downstream. All right, so here's our quick picture of the two, and our two mechanisms now are plucking and 2 is abrasion. Abrasion is the easier one to picture. This is like sandpaper, but it is rock plus sand that's in the ice, held in the solid ice. They just groove and polish the rock that they're riding over. And that's what's going on here. This is abrasion. And over here we have plucking. And what plucking does is that ice gets around chunks and then rips those chunks off and carries them away. And so we'll say this: ice surrounds plus removes. And this can be quite an efficient process to strip a landscape. The next thing I want you to be thinking about is the movement. And we'll do one more quick sketch here. Here's a mountain range. Again, this could be a continental ice sheet as well if you wanted to think about Antarctica or Greenland instead. But here is our glacier, and the glacier is flowing downhill. I would like you to picture this as a conveyor belt. That's awful. Conveyor belt that is moving material from this erosional area, which tends to be higher up, and it's moving down to the deposition. So deposition is occurring at the toe, and so we are going to build deposits of glacial material at the toe of glaciers, and we're going to be creating erosional landscapes near the upper regions. And so what I'm going to do now is I'm going to go through 2 lists. I'm going to throw in pictures at the end of these lists to anchor. All right, so we're going to start off here with erosional features. And bear with me if you can't picture them as I'm first describing them, because we'll throw in pictures last. The first, number 1, is going to be striations, grooves, polish. This is a small scale feature, but you can see it in glaciated terrains. Number 2 is a cirque. Number 3 is an erode. These are French names because these were described in the Alps. These often occur together. Now, a cirque is a bowl, and so it's a bowl-shaped depression on side of mountain. And these are like the headwaters of a glacier. This is where glaciers are born. That's kind of a neat thing about a cirque. An erode is a knife-like ridge. If if you have a glacier on one side and like one valley, and you have a glacier on another valley, they're carving towards one another, and they can create these knife-like ridges. And so cirques and bowls are occurring high in mountains, and they're associated with one another. Number 4 is a U-shaped valley. When a glacier carves a valley, it forms in a U shape because when erosion occurs, it removes sides of the valley plus the bottom, both of them at the same time, which creates this U-shaped bevel. Now this is different than a river. When a river erodes, it erodes with a V shape because erosion is occurring in a river at the bottom. And so when you're in a valley that is carved by a river versus a glacier, you can recognize it by the bevel or shape of the valley itself. A fjord, these are very simple. It's a U-shaped valley filled with water. So this is U-shaped. So this is just near sea level. We could say submerged would be another way to say it. It's a submerged U-shaped valley. And then the last feature that I want you to know, that these are erosional features of material being carved away. It's called a drumlin. And a drumlin is a sculpted hill. It's aerodynamic. Let's say molded hill. Aerodynamic. Now you can look up any single one of these words on Google Images and find really neat pictures, or Wikipedia. I'm just going to insert some right now to give you a chance to see them, and then we'll move on. So here in this first picture, we've got grooves and striations. All right, you can see, oops, here we go. Grooves and striations carved by ice just grinding away over the surface. The ice is gone, but the evidence is there. And here, these features are hills, but they've been molded into these aerodynamic shapes by ice flowing over them, maybe like in this direction. All right, that's a drumlin. All right, next picture. What do we got here? We got a mountainous region. This is actually in Antarctica, but we have got arêtes and cirques. So this bowl-shaped feature, that is a cirque, and here would be another cirque, and here would be another cirque. It's these, here's another cirque. They're everywhere. They're being carved in where glaciers are being born, and then the ice is flowing away from those regions. And then look at the knife-like ridges throughout this entire picture. All of these ridges here we could call an arête. All right, next picture, U-shaped valley. This probably defines itself very nicely for you. Look at that. Look at that curvature. There's the U. And this one you could argue is also a fjord because part of it has water, but then up here, notice up here it's dry. So there's a U-shaped valley, and this would be the fjord down here. And that is it for the pictures of erosional landscapes. So now let's move on to depositional features. Depositional features are landscapes. There's going to only be two here that I'm going to emphasize. The first is till, and the second is a moraine. A moraine's even made of till. But so what till is, it's a glacial sediment. A glacial sediment deposit. And this looks very different than a river sediment deposit or a wind sediment deposit because the ice doesn't care how heavy things are. And so it mixes particle sizes completely together. In geology, we call that mixing very poorly sorted. It means that gravel is mixed with sand, mixed with silt, mixed with boulders even. And so we could draw that with circles of different sizes, all mixed together. And here's the little dots showing that it's all mixed together. And that has to do with just ice is solid and carries all these things equally, whereas a river can't carry a boulder and a grain of sand in the same way because the water's not strong enough. A till is deposited either below a glacier or at its edges. I'm going to insert a picture here for you of glacial till before we move on, just so you get an idea for what I'm talking about. Change the color. So here's what we have. This right here, this kind of snake-like positive feature, this is composed, all this in this area here, this is all composed of till. And what I want you to see is that there are big chunks in it, and then there's fine-grained things. This one, this deposit here, was deposited at the edge of a glacier, which is why it's a positive topographic feature. This area in here is also till, but it was deposited below a glacier. Okay, now let's talk about moraines. A moraine is a positive topographic feature. It's a hill. Positive topographic feature that forms at the end. We might call it a terminus. So positive topographic feature that forms at margins, that's a better word, margins of glacier. What they do is they mark the margin. Let's even say that. They mark the margin. And I want you to picture the glacier as a bulldozer that is moving sediment, moving sediment, moving sediment. Specifically, let's call it till, because that's what glacier sediment is. And so the actual positive topographic feature that marks the edge of a glacier, here's our glacier, right? The glacier is flowing downhill. This is in Greenland. And this feature right here, that used to be the edge of the glacier, and the glacier sat there for a long time, and the conveyor belt of glacial till being brought down this hill piled up and piled up and piled up along the margin to create this positive topographic feature. When you're at the end of a glacier like this, it's called a terminal moraine. When you're at the sides like this, this is called a lateral moraine. And in fact, if you have like two glaciers that come together, so imagine we're in a bird's eye view, and here is a glacier, and here is a glacier, and they merge into a single glacier, then you would have, okay, and let's have here's the end of that glacier. There would be a terminal, here's your terminal moraine, here's your lateral moraines building up on the sides. And then when they come together, you can actually get this thing in here in the middle that's called a medial moraine. And they are just deposits of till. These have been mapped across much of North America, wherever glaciers have been. And in Texas, we don't see these, but if you were to live in Chicago, Detroit, Minnesota, these are really important features, both moraines and tills. And so they're deposits from the last ice age. So, and it allows pictures like this to have been created. Where how do we know where the glaciers were at the extent of the last ice age? Well, the extent of the terminal moraines allow that to be mapped. And all of this material that the farms and the cities of this area of the world are built on, they're built upon deposits of till. It's different than the limestones for where we live here in Texas. Okay, so those are our two different types of landscape makers. And then to finish off this lecture and to finish off glaciers, I just wanted to take you through three big concepts. Okay, so let's go down here. Okay, three big concepts that if I didn't introduce to you, it would be remiss, it would be bad teaching. And so one of them is going to be glacial floods. These have happened in the past, these have happened in modern history, and what ends up happening to make a glacial flood is that ice can dam a river. And if a big glacier of ice dams a river, it can make a lake behind it. So we could say a lake builds up. But a glacial dam is not a stable dam. It's not permanent. And so that glacial dam can lead to failure, and a failure will lead to a large flooding event. In the Himalayas, examples have occurred in the Himalaya in modern times, like there was one just a couple years ago. And this can be a natural disaster that impacts all the towns along that valley downhill. But in the long ago past, there is a place in the Pacific Northwest in Washington, and this is called the channeled scablands. In the channeled scablands, a large lake built up called Lake Missoula, and Lake Missoula emptied when the ice dam failed, and it sent a wall of water across all of the state of Washington. And it would have been a devastating event. Anyways, you can look it up if you want to. So that's one of the big concepts. The next big concept I want to introduce in glaciers is called isostasy. And we'll introduce it here as glacial isostasy. But it's this word isostasy that really matters, and it means gravitational equilibrium. Gravitational equilibrium. And basically, the surface of our planet is always trying to exist in gravitational equilibrium. And so if we have the crust, and it's this thin veneer on the outside of our surface, and it is sitting on top of the mantle, and the mantle is fluid in part. Well, if we build up a chunk of ice that's 5 kilometers thick during an ice age, that is going to be putting a very significant amount of load on the crust. And what will end up happening is the crust will deform and sag a little bit underneath that load. But if the ice melts, the crust will rebound and try to find that equilibrium. So for glacial isostasy, it's the seeking of equilibrium when the crust rebounds after ice sheets melt. And what's really neat is that this is happening right now today. Much of the northern, let's say Europe and Canada, is actually rising right now. Let's say north is rising at, you could just picture something like 5 millimeters per year, which in a given year you don't even notice. But the crust is rising, so it looks like sea level's going down. It puts castles and ancient buildings that used to be on the coast now far away from the water. It's a really interesting thing. But this concept of isostasy is a major geologic principle, and this is our first interaction with it, but we're going to talk about it again with plate tectonics significantly. All right, so that crust rebounds after ice sheets melt, and so you can imagine if this is elevation and this is time as a graph, we are going to rebound. But then if it overshoots, it'll come back the other way, and then it'll try to find its equilibrium. This is the concept of isostasy. The final, do I have pictures of these things? You bet I do. Let me show you some pictures of isostasy. This is cool. You can measure it in a variety of different ways, but here's an example of a castle in Scotland, and this castle in Scotland, so here's modern day sea level, but see this bench? This bench right here marks where the ocean used to be, and so this used to be sea level relative to the castle, but it's this increase in elevation that is the isostatic rebound. Isostatic rebound. They didn't build the castle that far away from the sea, they built it right on the sea. But this is rising up, and we can see the same thing with Roman era buildings too. And now here's a more natural, these stripes on the beach, these are showing that this land is rising relative to sea level, and each of the stripes are benches that mark ancient sea level. All right, the final topic that we've hit probably a little bit too hard, but just to have the last thing in our notes, is that we are in a period of modern glacial retreat. Everywhere we look, every glacier we look at, they are experiencing a zone of ablation that is dominant. We could say all glaciers in regression. So if you ever have a chance to go look at a glacier, go look. We don't know whether they're going to be there 50 years from now when we're old. So see a glacier and experience it. They'll come back again someday in another ice age, but right now we're in a period of modern retreat. The exception to that, there's one exception, it's Mount St. Helens. It blew in 1980. There's a glacier in Mount St. Helens that's grown. Anyways, let's skip that. All right. Thanks for paying attention. See you next time.